Right now, a wall of charged plasma is racing toward Earth at hundreds of miles per second. It left the Sun less than 2 days ago. When it arrives, it will collide with the only barrier standing between us and the raw energy of space, a magnetic field that is thinner and more fragile than most people realize. We treat Earth's magnetosphere like it's a solid dome bolted above the atmosphere, permanent, reliable, always on. But that's not how it works. The magnetosphere bends, it compresses, and under the right conditions it splits wide open, letting streams of solar radiation pour directly into the upper atmosphere, cascade down magnetic field lines, and interact with everything from satellite electronics to the electrical grid beneath your feet. This happens more often than most people realize, and certain times of year make it dramatically worse. In this video, we'll break down what's being thrown at us from the Sun, why equinox season turns our magnetic defenses into a weak point, and why the next few weeks could bring some of the most intense geomagnetic conditions in over 2 decades. The Sun doesn't just shine, it throws things. Every second, it releases a torrent of charged particles, protons, electrons, helium nuclei, streaming outward at roughly 900,000 miles per hour. That's the solar wind. It never stops. It presses against our magnetosphere constantly like a river flowing around a stone. But the solar wind is a background noise compared to what happens during a coronal mass ejection. A CME occurs when a sunspot group, a region of concentrated magnetic stress on the Sun's surface, becomes unstable. The magnetic field lines twist, snap, and release a massive cloud of magnetized plasma into space. We're talking billions of tons of material, sometimes accelerated to speeds exceeding 4,500,000 miles per hour. A CME aimed at Earth takes anywhere from 15 hours to 3 days to arrive, depending on its speed. When the leading edge hits the magnetosphere, it compresses the day-side boundary from its normal standoff distance of roughly 40,000 miles above the surface down to as little as 25,000 miles. The entire magnetic structure flexes inward. Shock waves propagate through the field. The night side stretches and distorts. And if the magnetic orientation of the incoming plasma is aligned just right, southward, opposite to Earth's own field, something dramatic happens at the boundary. Magnetic field lines from the Sun and from Earth snap together and reconfigure in a process called magnetic reconnection. It's the equivalent of a breach in a dam. Through that breach, charged particles from the solar wind funnel directly into the upper atmosphere, spiraling along field lines toward the poles. That's what causes the aurora. Oxygen and nitrogen atoms in the upper atmosphere get struck by incoming particles and release light. Green curtains, red arcs, purple fringes. All of it is the visible signature of a crack in the Earth's magnetic defense. There's a pattern buried in a century of geomagnetic records. The most powerful storms cluster around 2 windows every year, March and September, both equinox months. This is not a coincidence. It's a consequence of geometry that most people have never heard of. Earth's rotational axis is tilted 23.4 degrees relative to its orbital plane around the Sun. During the summer and winter solstices, that tilt aims one pole towards the Sun and one away. The orientation of Earth's magnetic dipole relative to the incoming solar wind is skewed. The connection between the two fields is inefficient. Solar wind particles slide past without engaging fully. During equinox, the geometry shifts. Earth's tilt axis sits perpendicular to the Sun-Earth line. This means the magnetic dipole presents itself in a way that allows far more efficient coupling with the interplanetary magnetic field carried by the solar wind. Geophysicists call this the Russell-McPherson effect, and the numbers are striking. During equinox months, Earth's magnetic sphere extracts approximately 40% more energy from the solar wind compared to solstice months. The direct consequence, roughly twice as many geomagnetic storms during equinoxes versus solstices. Electron flux in the radiation belts can spike anywhere from 3 to 12 times higher than during solstice periods. And here's where the timing gets critical. This effect is amplified during solar maximum, the peak of the Sun's roughly 11-year activity cycle, when sunspot groups are most numerous and CME launches are most frequent. We're not in just any equinox window. We're sitting inside equinox season at the tail end of solar cycle 25's maximum, the most energetic solar maximum since cycle 23, which peaked around 2001. Cycle 25 has already surpassed its predecessor, cycle 24, in both total sunspot count and the frequency of M-class and X-class flares. M-class flares are the second strongest category. X-class flares are the most powerful. Both have been firing off with regularity since late 2024. Some of the most significant flares have originated from massive sunspot groups spanning areas larger than Jupiter's diameter, regions of such intense magnetic complexity that multiple eruptions can occur within hours of each other. When multiple CMEs launch in rapid succession along similar trajectories, they can stack. The first impact compresses and weakens the magnetosphere. The second arrives while the field is still recovering. The third can push the system into severe geomagnetic storm territory, G4 or G5 on the 5-point NOAA scale. A G5 storm is the highest classification. The last confirmed G5 event was the Halloween storms of October 2003, which damaged satellites, forced airline reroutes, and caused a blackout in Sweden. Before that, the March 1989 event that collapsed Hydro-Quebec's grid. These are not theoretical risks. They are documented consequences of conditions very similar to what we're seeing right now. Trailing behind the CMEs, coronal holes, regions where the Sun's magnetic field opens outward into space, are rotating into Earth-facing positions. These holes release sustained high-speed solar wind streams that can keep the magnetosphere disturbed for days after the initial CME shockwave has passed. It's not a single punch, it's a combination. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. The aurora is the visible sign, but beneath the light show, energy is being dumped into the ionosphere, the electrically active layer of the atmosphere between roughly 50 and 600 miles above the surface. That energy heats and expands the upper atmosphere, which increases drag on satellites in low Earth orbit. During the May 2024 G5 storm, some satellites experienced measurable orbital decay in a matter of hours. The geomagnetic disturbance also induces electric currents in the ground, geomagnetically induced currents or GICs. These currents flow through anything long and conductive: power transmission lines, oil and gas pipelines, railroad tracks, undersea fiber optic cables. In 1989, the GICs from a G5 storm overwhelmed transformer protections in the Hydro-Quebec system, causing a cascading failure that left 6 million people without power for 9 hours. Modern grids are more interconnected than they were in 1989, which is both good and bad. Better interconnection allows rerouting around failures, but it also means that a disturbance in one region can propagate farther and faster through the network. The vulnerability hasn't disappeared, it's just been redistributed. GPS accuracy degrades during geomagnetic storms because the ionospheric disturbance alters the speed at which GPS signals travel through the atmosphere. High-frequency radio communications, which bounce off the ionosphere, can be disrupted or blacked out entirely in polar regions. Aviation routes over the Arctic are sometimes rerouted during severe events because crews lose reliable communication and navigation. There's an additional variable that formal space weather forecasts rarely mention: the moon. During new and full moons, the Sun, Moon, and Earth align. This produces spring tides, the strongest ocean tides of the lunar cycle. But tidal forces don't stop at the ocean. The solid Earth also deforms. The ground beneath you rises and falls by roughly 12 inches twice daily during these alignments. That displacement creates micro-fractures in the crust. Along faults that are already near the failure threshold, those fractures can act as a final nudge. Statistical analyses show approximately 0.5 to 1% more seismic events clustered around new and full moon phases compared to the monthly average. When a new moon coincides with a CME impact during equinox season, multiple forcing mechanisms stack simultaneously. Solar-driven ionospheric heating increases from above. Tidal stresses increase from below. The global electric circuit, the continuous flow of current between the ionosphere, atmosphere, and ground, gets amplified from both directions. Does this guarantee dramatic consequences? No, but it means the energy environment surrounding our planet is under more simultaneous pressure than during any single factor alone. And historically, some of the most geophysically volatile weeks have fallen inside exactly these kinds of convergence windows. The sun is not calming down. Even as solar cycle 25 begins its slow descent from peak activity, the transition phase remains hazardous. Some of the largest flares in recorded history have occurred during the declining phase of solar cycles, when the magnetic field configuration becomes increasingly complex and unstable. Several large coronal holes are rotating into geo-effective positions over the coming weeks. Each one is capable of launching multi-day high-speed streams. Meanwhile, a sun-grazing comet is approaching perihelion in early April, passing within roughly 240,000 miles of the solar surface, closer than the Earth-Moon distance. When comets pass that near the sun, their interaction with the corona and the solar magnetic field can produce unexpected electromagnetic disturbances. Whether this specific comet triggers additional eruptions remains unknown, but the timing places it squarely in the middle of an already volatile window. A second comet reaches perihelion in mid-April and enters a near-perfect Sun-Comet-Earth alignment around April 23rd. Observations over the past 2 decades have shown that when comets are positioned along the Sun-Earth line, there's a statistical uptick in CME activity directed toward us. The mechanism isn't fully understood, but it appears related to electromagnetic interactions between the comet's plasma tail and the solar wind. So the picture through the end of April looks like this. Continued high flare activity, stacked CME potential during equinox season, coronal hole streams sustaining geomagnetic disturbance, and at least 2 cometary perihelia that could add unpredictable solar responses on top of everything else. The practical takeaway is straightforward. If you live at high latitudes, aurora forecasts are worth checking nightly. If you manage critical infrastructure, power grids, satellite operations, pipeline monitoring, review your GIC mitigation plans. And if you pay attention to how the space environment affects weather patterns, seismic trends, and even human psychology, the next several weeks deserve close attention. The magnetosphere is the only thing standing between 8 billion people and the full electrical output of a star. Most of the time it holds, but during equinox, during solar maximum, during stacked plasma impacts, it bends and cracks in ways that remind us exactly how thin that shield really is. We talked about what the sun is throwing at Earth, but something else has been falling from the sky, and nobody can explain where it's coming from. 7 fireballs in 20 days. 3 drop recoverable fragments. None match any known meteor shower. Watch Why Are So Many Fireballs Striking Earth and Exploding Right Now to find out what's going on.